it, right?
Yes.
Okay,
Yeah.
awesome. So the changes either happens to X, the input, or happens to the output Y. Let's look at this problem. We have two functions. Function f of x is the mother function. The mother function is a set of ordered pairs. When the input is -2, output is 0. When the input is -1, corresponding output is -1, and so on. So that's how do we understand function f of x from this table. F of x is given by using this table. Hx here is the daughter function. And let's compare the two functions. Notice they have the same domain. The first row in the two tables are exactly the same, right? So the domain elements, the inputs are exactly the same. The difference happened to the output. The difference happened to the output. For the same input, when output of f is 0, output for h is a -1, 1 less than 0. For the input -1, the output for f is -1, but the output for h is -2, also 1 less than the output for f. You can see the pattern continues, right? When the input is 2, the corresponding output for f is -3, the corresponding output for h is 1 less than -3. So the pattern shows for the same input, the daughter function always produce output that is 1 less than the output of the mother function. So the change happens to the output. What's the change? Less than 1, right? -1, the change is -1. And -1 happens to the output. So we choose this option, okay? -1 from the function, from the output. X is the input inside the parentheses. F of x represents y. We know f of x is y. Y is the output. So the change happens to the output. So the daughter function h of x is 1 less than the mother function, f of x -1. And let me know, is that clear? The idea seeing function as a machine still works when we consider transformations. In this case, the input remains the same. The output changes. All the values of the output become 1 less than the mother function's output. So the change happens to the output. We have 1, we subtract 1 from the output of the mother function f of x. And that's question 1. Question 2. If the formula y equals x to the power 3 is changed by adding 4 as shown in red below, which values would be most directly affected by the change? By the way, this function y equals x cubed is called cubic function or cube function. This machine always produces output that is equal to the cube of the input. It's a very basic function. It is called a cube function. The output is always equal to the cube of the input. And that's the mother function. And this is the daughter function. We already applied the treatment. What's the treatment? We added the 4. We added the 4 to x. We added 4 to the input of the mother function, right? So the change happened to the input. It's important to identify does the change occur to the input or output? In this case, the change happened to the input. Since it changed to the input, it has the impact on x. So let's see what do we have here. It will directly affect x values. It would directly affect y values. It would have no effect. Of course, we do not choose the last option, right? It does have a certain impact, and the impact occurs to x. Okay. In order to produce the same output, all the x values have to be 4 less than the original. So when we add a 4 to x, remember the graph, how does the graph change? The graph would shift to the left 4 units, right? It happened to x. What effect would it have to on the graph? As I mentioned earlier, it would shift all the points to the left 4 units, right? To the left 4 units. So press again. That change happens to input. When we add a 4 to the input, x values are directly affected. The graph of the function is going to shift to the left 4 units. Number 3. So the daughter function g of x is f of negative x. F is the mother function. So the transformation is we multiply -1. We multiply the input by -1. When we multiply input by -1, the graph flipped with respect to y-axis, right? And here, we don't really have a graph. Function f and the function g, they are both given as a table, So function f is given, the inputs and the corresponding outputs, and we need to fill in the tables for function g. G is f of negative x, all right? So since the -1 is multiplied with the input, since the -1 is multiplied with the input, x values will be directly affected. X value will be directly affected. So what's the change to the x values? All the x values are going to become their opposites, right? All the x values are going to become their opposites. X is -4, here is going to be +4. -3 going to become +3. Oh, sorry, +3. +11 become -11. -6 become +6. So when all the inputs become their opposites, the corresponding outputs remain the same. The change only happens to inputs. The outputs are not directly affected. So we're gonna copy the second row. The second row for G would be the same with the second row of F. 13, 6, 4, -5. Okay, so submit, right? Number 4. This is called a square root function, right? This is the square root function. You might remember we analyzed this function's domain and range. Both of the domain and range of the square root function are 0 to infinity. 0 is included. So all the inputs have to be bigger than or equal to 0. All the outputs also have to be bigger than or equal to 0. And G and H are transformations of f. So mother function has $2. Run the formulas for G and H. Be sure to use proper function notation. Okay, let's see. We are looking at the 3 functions, right? We are looking at 3 graphs. Function f is the square root function. As you can see, the graph only appears in quadrant 1 because both of the domain and range are bigger than or equal to 0. So it only appears in quadrant 1. Function g, the first daughter, is a transformation of f. Let's see what's the change. What's the change? So seems like the graph is flipped, is reflected over x-axis, right? Yeah, the graph is flipped over x-axis. What kind of transformation will make that happen? G of x. So we should enter G of x. The first daughter function is going to be negative f of x, or rho x here. All right, the first daughter G of x is is a reflection. Yeah, G of x is a reflection of f of x with respect to the x-axis. G of x is a mirror. Like if we see the x-axis as a mirror, and the G of x is a reflection of f of x. Do you guys see it? When you flip something, when you flip a graph from top to the bottom, or from the bottom to the top, that is a vertical change. That change happens to y values. That's the reason we multiply the whole function, y value, by -1. H of x. When we look at the h of x, we ignore g of x, okay? H of x is the daughter of f. So when it comes to transformation, we do not consider g of x anymore. So consider the relationship between f and h. And look at the graphs. Since h of x is the reflection of f of x, when f of x flip over the vertical scale, if you see the vertical scale as the mirror, the reflection of the square root function would be h of x, right? So when you flip something, when you flip the graph from right to the left or from left to the right, that change happens to x, because that's a horizontal change, right? Yes, in this case, the change happens to x. What kind of change? We multiply x by -1. That's the change. So function square root of x, the input is going to become -x. So we multiply x by -1. For g, we multiply y by -1, right? So let me summarize. When you multiply the output of the function by -1, you get the reflection of the original function with respect to the horizontal scale. When you multiply the input by -1, then you will have the reflection of the original graph with respect to the vertical scale. Knowing when you flip a graph from top to the bottom or from the bottom to the top, that change happens to y-axis. There's a vertical change. So the change happened to the output. When you flip a graph from the right to the left or from the left to the right, that change happens to x. That's a horizontal change. Since the changes happen to x, so you're going to apply the treatment to the input. Okay? Any questions so far? Yeah, I'm going to only spend 20 minutes on this. We have 2 more minutes. How about let's do one more here. And this problem, actually, we had this problem on a note, the guided note last Thursday. I think I can skip this one. Let's see. This one is different. G of x is the graph of f of x shifted right 5 units. Write a formula for g of x. So now we know mother function is f of x. G of x is going to be the daughter function with a certain transformation. What is the transformation? We shift f to the right 5 units. Okay, if we shift the function f to the right 5 units, we will have g. Can you give the function for g? And I'd like you to type your answer in the chat to see if you are with me. Shift to the right. Shift the mother function graph to the right 5 units. To the right, to the left, that is a horizontal change. The change is going to happen to x, right? Happen to the input. Shift to the right 5 units. Are we going to add a 5 or minus 5? We add a 5 to the whole function, or minus the 5 from the whole function, or add a 5 to x, or minus 5 from x. So consider those options. Please type your answer in the chat. Yeah, we should start to use the chat. Okay. Some of you, perfect. So Michael typed the answer g of x equals 3 times absolute value x minus 5. That's it. That is great. When you shift it to the right 5 units, you actually minus 5 from the original input. Thank you, Michael, for your response. And Kaida also provided the correct answer. Very good. Thank you, Kaida. I hope other 4 students, you understand the result, okay? So we have 3. Absolute value is right here. You don't have to type. So it is x minus 5. You minus a number from variable x, the graph shifts to the right. If you add 5 to the variable x, the graph should shift to the left. Here, shifted to the right, so we minus 5. All right, guys. So we spent 20 minutes on practicing a little bit of transformation. And now let's go back. The guided note. We're gonna talk about another topic in section 1.6. We're gonna talk about odd functions and even functions. I'm going to stop share this one and share my note. My word, it's right here. Okay. Our Lumen include the definition of odd functions and even function in this section 1.6. Now I'm gonna give you the definition for even function, odd function, right? Yeah, number 28. Grab my stylus. What is an odd function? What is an even function? Let me hide the floating meeting controls. Okay, very good. Say f of x has domain D, and we can use D of parentheses of f to represent the domain. If the following 2 conditions are met, I'm going to write the 2 conditions. Then f of x is an odd function, right? So let's give the definition for odd function first. For a function to be an odd function, 2 conditions must be met, must be satisfied. The first condition, the domain, I can just use D. Let's just use D. The domain is symmetric with respect to the origin 0. So here W dot R dot T dot is just a short way abbreviation for with respect to 0. Yeah, what does that mean? Let's say f of x equals x squared. This is a parabola, right? The graph is a parabola. And also this function is a very simple polynomial function. A while ago, I made you to take a note and write down a conclusion. The domain for any polynomial functions is all real. So the domain for this parabola, for this square function is also all real. The domain is net infinity to past infinity. So on the real number line, let's say this is 0. That's the origin, right? So the domain is the whole real number set. And as you can see, the whole real number set, it is symmetric with respect to 0, right? And what if the domain of the function is, let's say, another function? It's going to be different, right? G of x. g of x equals x squared, the domain is, or x cubed. The domain is, let's say, -1 to +1. Okay? Domain is -1 to +1. And on the real number line, if we graph the domain, this is the origin, this is -1, this is +1, the domain is going to be an interval, left open, right closed. And is this domain symmetric with respect to 0? Is this domain symmetric with respect to 0, the origin? Pretty close, but, you know, pay attention to the details. What do you think? Let's say we have a function. Here we are talking about the domain, the symmetry of the domain. If the domain is from -1 to +1, left open, right closed, is the domain counted as symmetric or not symmetric? Are you guys with me? Huh?
Yes,
Yeah.
So symmetric or not symmetric?
Not symmetric?
You're right. It is not symmetric because the left endpoint is excluded, but the right endpoint is included, right? This is symmetric. 1, 1, both open, or both closed. That is symmetric, all right? So in order to be an odd function, the domain has to be symmetric with respect to 0. This is a condition a lot of people tend to ignore and make a mistake on. And let's look at the other function. Let's say this function. We have seen this function last class, right? It is the square root function. Earlier, I also emphasized the domain of the square root function is from 0 to infinity. Is this domain symmetric? Is this domain symmetric? Symmetric with respect to the origin. On the real number line, if I graph the domain for the square root function, it is a ring, you know, the region is like a ring. All the points in that region are domain elements. Obviously, it's not symmetric, right, guys? So if a function whose domain is not symmetric with respect to the 0, we do not talk about odd or even at all because the first condition is not met. So definitely it's not odd function or even function, all right? In order to be an odd function or even function, firstly, their domain has to be symmetric with respect to 0. If that condition is not met, we don't even consider. And to be an odd function, besides the domain has to be symmetric with respect to 0, another condition must be met. The other condition is for any domain elements in D. Okay, just no, this is a means belong to. Okay, means belong to. For any domain element in a domain, f of x equals negative f of negative x. Okay, I can actually address a different way. After f of negative x equals negative f of x. This is the center. This is the center of this definition. A very important condition. An other function has to met. F of negative x has to be equal to negative f of x. F of negative x has to be equal to negative f of x. So what does that mean? We can try to use the transformation to understand the graph of the function. So on the left side, basically, we flip the graph of the function f over y-axis, right? Over y-axis. And on the right side, we actually flip the graph over x-axis. So it means If you have the graph and you flip the graph over x-axis, and the result would be the same with when you flip the graph over y-axis. Okay, and what type of function satisfy that condition? I can give you an example. F of x equals x cubed. The cubing function is an odd function. Okay, because for one, the domain is all real. Net infinity to past infinity, symmetric with respect to 0. For two, if we find f of negative x, which is negative x to the power of 3, and that gives us negative x times negative x times negative x. Negative x times negative x is positive x squared. Positive x squared times negative x is negative x cubed. And x cubed is f of x. So we proved the second condition is met as well. For any x, f of negative x and the negative f of x, they are the same. They are the same, okay? I need more space here. And also, let's look at the graph of the cubing function. The graph of cubing function passing through 0, 1, 1, and negative 1, negative 1. Hide this. So the graph of a cubing function looks like this. All right. If we flip the graph with respect to x-axis, we will have this graph. If we flipped the red graph, the red curve over y-axis, we got the same thing, right? So that's the condition this condition means. And that tells us the graph of an odd function. Note the graph of an odd function is symmetric with respect to the origin, 0, 0. What does that mean? That means if we rotate the graph 180 degrees, the graph would coincide with the original graph. So this curve is the graph of cubing function. And we already checked cubing function x cubed is an odd function. Domain is symmetric, and this condition is met, right? And the graph of this function definitely is symmetric with respect to the origin. You can imagine if you rotate, let's see if I can do that. If you rotate this curve, rotate the curve, like, no, I don't think I can do that. So you can just imagine in your head, okay? Rotate 180 degrees, you will have the same curve. You see what I'm talking about? Any curve, if the curve after rotate 180 degrees, would the graph would coincide with the original graph, and the function is an odd function. So here I want you to know those characteristics of odd function. For an odd function, 1, the domain has to be symmetric. 2, this condition has to be met algebraic wise. F of negative x equals negative f of x. 3, graphically speaking, in geometry, the significance of the geometric significance of odd function is the graph of the function is symmetric with respect to the origin. That means if you rotate the function, the curve, 180 degree, the curve, you know, the resulting curve overlapping, coinciding with the original curve. All right, do you see those three things about the other function? Domain, and this algebraic significance, and the geometric significance. So far, so good, guys? Any questions about other function?
Nope.
Yeah, that's in theory, that's how much it takes to explain the definition of other function. Okay, now I'm gonna give you the definition for even function. Say function, can I still use f? Let's still use f. Is a function with domain D. If the two conditions are met, then f of x is an even function. You see the similarity between the two definitions, odd and even. The first condition is exactly the same with earlier. Domain is symmetric with respect to 0. Second condition, for any x in the domain, f of negative x is the same with f of x. And this is the center, the focus of this definition. And that's the only difference between the two definitions. That condition is for a function to be odd, and this condition is for a function to be even. All right, for a function to be even, besides the domain is symmetric, when the input become is opposite, the corresponding output is still the same. And if we think about the graph, we know if this is the mother function, then this would be the reflection of the mother function with respect to what? Y-axis. From right to the left or from left to the right, that is the change in x, right? Yeah, with respect to, this is the reflection of the mother function with respect to the vertical scale. So what kind of graph would meet that condition? The graph of an even function is symmetric with respect to the y-axis, with respect to the vertical scale. For example, f of x equals x squared, the square function. Domain is all real as a polynomial function. Domain is all real symmetric. And if we compute f of negative x, if we change the input to negative x, and the output would be square of negative x, and you know negative x times negative x is still positive, right? Yeah, positive x squared, and which is the same with f of x. So the second condition is met as well. And on top of that, let's look at the graph of the square function. The graph of square function, we all know that's very basic. You really need to know the square of the graph of the square function. It looks like this. Okay. The vertex is in the orange. So this graph is symmetric with respect to the vertical scale. So if you flip, or if you flip this graph with respect to the y-axis, you have the same thing. In other words, the reflection of the graph with respect to the y-axis is itself. You see what I'm talking about? Yeah, this part would be the reflection of the other side, and this side would be the reflection of the other side. After the sides reflect, it's still the same graph. So in order to satisfy that condition, this condition, f of negative x equals f of x, the graph must be symmetric with respect to the vertical scale, y-axis. So about even function, three things. Number one, domain symmetric with respect to 0. Why am I emphasizing that? Sometimes, for some reason, very easy for people to forget that condition. And let's say if I give you a function and ask you to determine, is this function odd or even? You do not spend time to check this condition or this peak condition, all right? Because you know this function is not gonna be even or odd. Why not? Because this square function has a domain 0 to infinity. It is not symmetric. For that reason, it is not odd or even. So we don't even have to check the condition, you know? Definitely not. So that's number one, domain of even function symmetric. Number two, for if we take the opposite of the inputs, the corresponding outputs are the same. Outputs remain the same. So f of negative x equals f of x. Number three, geometric significance. The graph of any even function is symmetric with respect to y-axis. So I want you to know the three things for even function and the three things for odd function. When we talk about odd function, you want to right away think about the graph of the cubing function. Yeah, this is a good example. It is a good idea. You connect one concept with a very simple example. Every time you need to handle, you need to deal with the concept. You think about the example, very simple. It's easy to remember, and all the features, characteristics will help you to, remember the definition, the concept. So when we talk about odd function, we want to think about the cubing function, right? When we think about even function, the square function is a good example. All right, let's do problems. Number 29. For each equation below, determine if the function odd or even or neither. Okay. So this is a quadratic, this is a polynomial function, right? F of x, polynomial function. Remember, domain of polynomial function is all real. Okay, so symmetric, no problem. And we're gonna have to check if f of negative x same with negative f of x, right? So that's the condition for even or odd. That's condition for odd. Okay, so let's see what is f of negative x. So start from calculating f of negative x. F of x is 4x minus x cubed. So when the input becomes the opposite of x, we're gonna replace all the x with negative x. So we have 4 times the input minus the input to the power of 3. All right, and then simplify. 4 times negative x, negative 4x, minus, okay, let's see what it is. Slow down. It does take a lot of algebra in pre-cal, and pre-cal assume you are very skillful with those things. Negative 3 to the power of 3, negative x to the power of 3, negative x, negative x, negative x. Negative x times negative x, positive x squared, times negative x. Positive times negative is negative, so negative x cubed. So this part, the yellow part, is a negative minus negative x cubed. Be very careful when you have minus negative. Be very careful when you have minus negative. So we have negative 4x plus x cubed, right? Plus x cubed. All right, so let's see what is the f of negative f of x. Obviously, f of negative x is not the same with f of x. So it's not going to be even, right? For sure, it's not going to be even. So let's see if it's odd. What is a negative f of x? the opposite of the whole function. So we're going to take the opposite of the output of 4x minus x cubed. We distribute. When we distribute with the coefficient -1, we just remove the parentheses and with all the members change to its opposites. So positive 4x becomes negative 4x. Negative x cubed becomes positive x cubed. Okay, look at that. Look at what we have. They are the same, right? So for function f, we proved the domain is symmetric and f of negative x is the same with negative f of x. And those are the two conditions for other function. So this is an other function. This is an other function, all right? Okay, that's the first one. Any questions, guys? We use definition to check, to determine if the function odd or even. We start from calculating or finding f of negative x. We start from finding f of negative x. Now let's look at the g of x. What's the domain of g of x? Domain is all real, okay? How do I know? Again, mainly when we find the domain for a function, we are trying to find the restriction on the input. If you have no restriction on the input, then the domain is going to be all real. So this function has no restriction. There's no square rule, has no denominator, so it's all real, okay? And the same with earlier, we are going to, I need to find some space. I'm gonna do this here. I'm gonna start from g of negative x, all right? G of x is the absolute value function plus 4. So the input now is gonna be negative x. Take the absolute value of negative x and then plus 4. We know absolute value of so absolute value is always non-negative, right? If the inside is a positive, it is a positive. If the inside is negative, it's still positive, right? So we can understand this part as absolute value of -1 times absolute value of x. And we know absolute value of -1 is 1, so it's the same thing, right? Do you see that? It's the same thing. Equals g of x. So we proved, or we found out g of x satisfies g of negative x equals g of x. It is even. It is even, right? And how do we know? Another way, another actually faster way, just for this function g of x to know it is even, is look at the graph of g of x. G of x is a daughter function of the absolute value function. Absolute value function is this. Remember that? And then g of x is absolute value function plus 4. So we just need to shift. We just need to shift the absolute value function, the V-shape graph, upwards 4 units. 1, 2, 3, 4. And that transformation does not change the fact the graph is symmetric with respect to the y-axis, right? So it's still even. It is still even. The mother function, absolute value function, is even because it's symmetric with respect to the y-axis. And if you shift upward or downwards, it doesn't change the symmetry. So it is still even. So either way, from the graph or from the condition, geometric, the algebraic condition, function g is even, okay? And number 3, h of x. I don't know if you know how to find the domain for h of x. The domain of h of x is all real except 0. Remember when I said when we find the domain, we mainly focus on trying to find the restrictions of x. X cannot be what values. We just need to exclude those values from the all real, right? And in this case, not 0. So we exclude 0 from the real number set. So the domain is negative infinity to 0, union 0 to plus infinity. All right? It's still symmetric, by the way. it is still symmetric. And we are going to see what is the h of negative x. We just need to replace the input with negative x. All right? And this would give us negative 1 over x plus 4. And it is not same with h of x, and it's not the same with negative h of x either, because negative h of x is going to be negative 1 over x minus 4. By the way, this is not algebra class. Algebra is the prerequisite course of this pre-cal. Those calculations, for example, multiply function h by -1, you're supposed to get that done quickly, all right? Multiply the function by -1, so each part become its opposite, negative 1 over x minus 4. So it's different, h of negative x is different from negative h of x either. Since none of the conditions are met, so this condition is not met, this condition is not met, we know h of x is neither, okay? H of x is neither. We start from 9:30, so now it's 10:20. We have another 30 minutes. Okay, so we are going to only cover one question about even and odd, and it is actually pretty comprehensive. Anybody want to know what's the graph of h of x? So this function y equals 1 over x is also a very basic function. This function is called a reciprocal function because the output of the function is always equal to the reciprocal of the input. It's called a reciprocal function. If you already started section 1.6, you can see it actually requires the name of this function, reciprocal function. What's the graph of the function? You need to please remember the graph of the function. All right. The graph of the reciprocal function only appears quadrant 1 and quadrant 3. In quadrant 1, we have a branch. This here should pass 1, 1. In quadrant 3, we also have a branch passing -1, -1. And our h function right here, our function h, is a dollar function of this reciprocal function. The transformation is to add 4 to the whole function. So basically, the graph of h of x is going to be this hyperbola shaping upward 4 units. Okay, so actually, this reciprocal function is odd. However, if you shift it upward 4 units, it's not going to be odd. It's not going to be even either. Do you guys see it? Yeah, I wish that I can see you. Because if I make you to show your face on the camera, it will only make the system slower. I remember one time I had to restart a computer. I don't really feel good about it. So I will not make you to show your face, but I would appreciate if you once in a while respond me. Is this problem clear? Everybody, number 29?
Yeah, it's clear.
Awesome. Very good. Perfect. Very good. All right. So that's everything about section 1.6, or almost all the things. Okay. Almost all the things. So now let's start section 1.7. What do we do in section 1.7? We're going to talk about inverse function. Inverse function. Gonna have more space. This part. I'm gonna put this part, see if I can get this part. No, I'll just erase them. Just erase them. Reciprocal function. Okay. Inverse function. Let's start from number 30 to determine determine the condition for a function to be invertible. Okay, invertible. Number 30, we need to answer this question. What is an invertible function? How do we know if a function is invertible? So first thing, we want to know what is one-to-one functions. Say y equals f of x, x is in D. Okay, hold on. Is a function. Say y equals f of x is a function. Say f of x is a function. If for any range element y in R here, initial of range, if for any output in the range, there is exactly one corresponding domain element in the domain, make a pair with it, then f of x is a one-to-one function. Yeah, this is the definition for one-to-one function. In words, if I write sentences to describe what is a one-to-one function, that's the definition. And make it easier for us. Make it easy for us. Remember, in order for a relation to be a function, for each husband, who is husband, by the way? X is a husband, right? X is a husband. Y is wife. Yeah, back to the beginning of the semester. In order for a relation to be a function, for each husband, the husband can only has exactly one wife, right? Yeah, that's the definition for a function. If the relation does not have a cheating husband, for any husband, there's only one wife. Okay, it is a function. But for a function to be a one-to-one function, one more condition needs to be met. Not only there's no cheating husband, but also we do not allow cheating wife. So basically, if we have a relation for any husband, there's only one wife. At the same time, for any wife, there's only one corresponding husband. Then the function is a one-to-one. Think about that. Every husband, there's only one wife. Every wife only has one husband. So 1-to-1, right? So the name exactly describes one husband corresponds to one wife only has one husband, right? So that kind of function is called a one-to-one function. Is that clear, guys? Not only for any domain element, there's only one corresponding range. For any input, okay. Not only for any input, there's only one corresponding output. For any output, there's only one input as well. So 1-to-1. Okay, do you guys remember vertical line test?
Yes.
Yeah. So we use a vertical line test to determine if a graph a function, right? If there's no vertical line cross the graph more than once, we say the graph passes vertical line test, then the graph is a function. Yeah, that's vertical line test. Now we are going to learn another similar test. It's called a horizontal line test. Horizontal line test, HLT. We can use a horizontal line test to determine if a function a one-to-one function. Very similar, very similar. I can give you some examples. Let's see, let's say this cubing function. This is the square function. This is the square root function. Remember that? This is the reciprocal function, two pieces. To graph the reciprocal function, it's better have a scale here. One branch here, one branch here. Right? Okay, so let's give 4 graphs. We're gonna use vertical line test and a horizontal line test to identify one-to-one function, like ideal functioning family with every wife only has one husband, every husband only has one wife. So in order to be a one-to-one function, the graph has to pass both vertical line test and horizontal line test. Let's see this one. This one passed vertical line test, right? And so it is a function. It is a cubing function, we know that. Does the function also pass horizontal line test? Do we have a horizontal line cross the graph more than once? If it is, this does mean my graph is not very accurate. It's supposed to like this, right? Like increasing. There isn't a horizontal line cross the graph more than once. So this cubing function is one-to-one. Okay, cubing function. Y equals x cubed. This function is one-to-one. 1, 2, 1. It is a one-to-one function. Okay. Now let's look at this square function. Y equals x squared. It definitely passes vertical line test, right? It is a function, square function. However, it does not pass horizontal line test. Those two, this wife has 2 different husbands. So not one-to-one. So y equals x squared, the square function is not 1-to-1. All right. And then the third function here is y equals square root of x, the square root function. And we can try the 2 tests. Pass this vertical line test, no problem, square root function. Also passes the horizontal line test, right? Yes, this is a one-to-one function. It is 1-to-1 function. This is a one-to-one function, all right? And now let's look at the reciprocal function. It passes, the function is y equals 1 over x. It definitely passes the, vertical line test. 1, 1, 1. There's no vertical line passes the cross the graph more than once. Similarly, if we try horizontal line, 1, 1, 1, 1, 1, 1. So there's no horizontal line cross the graph more than once either. So this is also one-to-one. One-to-one function, all right? So from the given 4 graphs, we identified 3 one-to-one functions. Why one-to-one function is so important? Because only one-to-one function is invertible. In other words, only one-to-one functions have inverse functions. So I'm gonna write this down, okay? Only, note, only one-to-one functions have inverse functions. At this point, we don't know what is inverse function. Just the thing about a function has inverse function means the function is invertible. The function is invertible. What does that mean? Invertible means okay. So how about let's use the machine. This is a one-to-one function. The one-to-one function, the machine is so as a function. When you give the function input, when you give the machine input, it will produce a corresponding output y, right? So for any x, you have exactly one corresponding y. But for invertible function, if you put a y back, you see y as input, put a y back, you will have x as the output, corresponding output. Of course, okay, how about this? Invertible function means the machine has a twin, 看到了一个 twin, not identical twin, like a different machine. And that machine, if you put a y in it, and it will give you the x. So you can understand an invertible function as a machine that has a twin machine. That twin machine produce exactly the input, the x, for any given y. So like you can reverse. Maybe I can describe this way. Let's say the machine, the input is a beef. A cow. So if the input is a cow and output is beef, right? So if we make the function invertible, that means it has a twin machine. If you put the beef back to the twin machine, the twin machine can get you the original cow. Of course, not every machine is invertible, right? It has to be very magical, has that power to convert the beef back to the cow, right? You can understand that way. You can understand like that. If that helps you understand the concept. Important thing is we know what is a one-to-one function. How do we determine if a function is one-to-one? And also know only one-to-one functions are invertible. In other words, only one-to-one functions have inverse functions. Okay, number 31, we are going to give the formal definition for inverse function. If you look at the video, you can take a screenshot of the notes. Sometimes I don't have enough space, so sometimes I thought I have enough space here, but it's just enough to write a little bit of thing. Okay, formal definition of inverse function. F, G are two functions. Okay, if for any x in the domain of x, in the domain of f, if for any x in the domain of f, g of f of x equals x, and for any x in the domain of g first and then f after also have x, then f and g are inverse function of each other. And we denote G as F inverse, and F is G inverse. This is the formal definition of inverse function. It might be not very easy to understand if you see a definition in a bigger paragraph, right? Just know the important part is this part. And I'm gonna use the assembly line to demonstrate that two things here, okay? I need more space here. Okay, so two conditions. Condition 1, condition 2, right? Condition 1 means for function f, it has a, for machine f, it has a twin machine, G. Means if you give any input to, if you start with any input in the domain of function f, and x, the input goes through f first, and then g after, and come out as itself. You see what I'm talking about? So whatever the treatment f has done to the input, g of x canceled that impact, reversed that effect, right? So let's say x is a cow, go through machine f, get a beef, and then the machine g actually has the power, has the magic to turn the beef back into the cow. If for any input, after the input goes through f and then go through g, and the final result, the final output is itself, that means g reverses f. G reverses f. Okay, this means g reverses f. Whatever f has done to the input, function g, the machine g, reverses that. That's why we have x come out as the output. You give a cow, and after that, you have a cow come out, right? So that means g reverses f. If the other way around also true, for any input in the domain of g, you don't have to worry about that. If the input goes through g first and go through f and come out with as itself, that means f also reverses g. Because whatever g has done to x, f cancel that effect. F reversed that. So that's why x come out. You see that? So if both of the two conditions are met, that means g reverses f, f reverses g, the two functions reverse each other, then the two functions are inverse functions of each other. And we have a notation. We can denote g as f inverse, we can write f as g inverse. The -1 on the shoulder of f means inverse, For example, this is you, okay? This is you standing here. You're standing here. If you go to the right 3 steps, and you'll be here, right? So how do you go back the original spot? Then you go to the left 3 steps, right? So in this example, walking to the left 3 steps reverses walking to the right 3 steps. And vice versa, you can see it easily. Walking to the right 3 steps also cancel, reverses walking to the left 3 steps. So those two processes reverse each other. So they are inverse of each other. In mathematics, we also actually saw something similar. For example, let's start from 7. I know 7 is a lucky number in this country. So if you add 2 to 7, and then minus 2 to 7, what do you have after the two things, after two processes? Do you still have 7? You will still have 7, obviously, right? Because subtracting 2 reverses adding 2. So adding 2 and subtracting 2, those two processes inverse of each other. Similarly, you multiply by 2 and then divide by 2. Those two processes cancel each other, reverse each other. You start from number 7, you multiply 2 and then divide by 2. You still get a 7. Or you start from 7, you divide by 2 first and then multiply 2 after. You still get a 7. Because those two processes cancel each other. Those two processes are also inverse of each other. Doubling, halving. They cut in half. Doubling, halving. They are inverse of each other. So I hope those analogies could help us to understand the concept of inverse functions. As functions, they reverse each other. And that's the definition of inverse function. Questions, please? Any questions?
No, you explained it really well.
Okay, thank you. As you can see, those two purple equations, they both need to be met in order to conclude the two functions are inverse of each other. So if a problem needs you to determine if two functions are inverse of each other, you do have to check those two conditions. And those two conditions involve composite function. But not too challenging. Remember, composite function is just an assembling line, right? More than one machines. See if we have a thing like that. Yeah, this one is. Okay, number 32 is the one that we need to use definition to check. F is given 3x minus 7. G is given x plus 7 all over 3. We need to determine if the two functions are inverse of each other. Okay, then we need to check those two conditions, right? We need to check those two conditions. The order doesn't matter. You can do this one first and then do this one. Or you can do this one first and then do this one. The order really doesn't matter, okay? We can try, how about, let's see, f of g of x. This is a composite function. Inside function g, outside function f. Remember, how do we do that? If the input is x, we're going to get rid of the inside function first, right? So get rid of inside function, replace g of x with x plus 7 all over 3. And this purple, I need a different color. This blue is the input. For function f, if the input is blue, the output would be triple of the blue minus 7. So input is blue, output would be triple of the input, the blue, and then minus 7, right? This is the blue. For function f, if the input is blue, the output is triple of the blue minus 7. Okay, now we're going to simplify this expression. This part, earlier I mentioned you need to have a good foundation from algebra, means you need to be able to quickly and correctly simplify those expressions. So we actually have x plus 7 divided by 3 and then multiplied by 3. So actually we have another inverse here. If this expression, this part, actually is x plus 7 divided by 3 and then multiplied by 3. Divided by 3, multiplied by 3 cancel each other. So we should have x plus 7. And then minus 7, we have x. Okay, one condition is met. After the input go through G and go through F, x comes out. We also need to check the other condition. This time f is inside function, g is outside function. Same with earlier, we get rid of inside function first. Inside function is 3x minus 7. I'm gonna color it as purple. So let's see how the machine G work. When the input is purple, not purple, pink. When the input is pink, the output of G is pink plus 7 and all over 3, right? Okay, so the output is going to be pink. This is the pink. Minus plus 7, and then all over 3. And let's simplify. Numerator, minus 7 plus 7 cancel, right? Those two processes cancel each other. So 3x on the top, 3 on the bottom. 3 cancels 3. Also, you see 3 multiplied with 3 here, divide by 3. Multiply by 3 and divide by 3. Reverse each other, cancel each other. So we have the x. Since both conditions are met, f and g are inverse of each other. All right, guys? And we finished the major part of inverse functions. We understand the definition and know how to use definition to determine if two functions are inverse. Next class, I'm going to show you how to find the inverse function of a given invertible function. And that will be on Thursday. Okay? So that'll be everything for today. Thank you guys for coming. If you have any questions, you are welcome to email me. Again, please do not email me in the Lumen. Please email me to my Outlook TCC institutional email. It's in the syllabus. I stressed that. Thank you, guys.
I have a question real quick.
Yes, please.
It's about the exam. Are we having any kind of a revision before the exam?
Review? Yeah, I will give you something to review on. How about let's look at the syllabus. Let's spend a little time to look at our syllabus.
Okay.
This is a pre-cal, is this one. Okay, this is our syllabus. Let me stop share this file and share our syllabus. This one. Let's see the last part. The last part of the syllabus is our schedule. Today is February 4th. We did not finish 1.7, but I mentioned this before. 1.8, we are not going to spend the whole 80 minutes. We can maybe spend half of the time. So next time when we met on Thursday, we can finish 1.7 and 1.8. And then next Tuesday, we'll do the review. And then I will arrange the exams after next Tuesday. You will have 1 week from February 11th to February 18th. You would have 1 week to work on your exam 1. Yes, we have a review session here. Did I answer your question?
Yes.
Yeah.
Thank you.
No problem. All right, guys, I'll see you on Thursday.
Bye. See you on
something to
Thursday.
say real quick.
Bye-bye.
See you on Thursday.
See ya.
What day is the exam due? I thought it was due on the 14th, correct?
I will probably give you until February 18th.
Okay, I thought it was due on the 14th. I didn't know you were doing the week. So I just scheduled my test for the 8th, this Saturday. That's going to be before the review.
You already
So.
scheduled the exam?
Yes, because I didn't know you were going to do that review. I thought that was the day of the test, not an actual review. So should I just cancel it and I guess try to do it on the 15th? Because I can't go during the week to take the test.
Can you email me? Where are you gonna take your test?
I was gonna take it at South East, because that's the only campus that does it on a Saturday.
Do you need to schedule a time? I think you can just walk in.
Oh, no, they're doing something new at the Southeast where you have to schedule for Saturdays. So
Oh,
that's why I was trying to get it in there early so that I could get a spot.
but 14th is not Saturday. 14th is Friday, right?
Yeah. So that's why I'm saying, is it okay if I try to take it on the 8th, or would you rather me just do the review and do it on the 15th?
I think you should start to think about your exams after we finish the review.
Okay. Okay,
Mm.
I will cancel it then.
Do not rush. Yeah, do not rush. And then also email me, shoot me an email, and I remember your situation. Okay.
Okay.
Thank you.
Yep.
Thank
Have a
you,
great day.
Alexia. Okay, bye bye.